Hello, my name's Gavin. I'm a sales support engineer at Nordson Sonoscan. In this video, I'm going to briefly explain AMI and its methods of non-destructive analysis. We can use AMI in any microelectronics application looking for delaminations, cracks, voids, differences in material density, anything ranging from BGAs, capacitors, QFNs. But specifically for this video, I have some examples of images inside a power module, an IGBT, and what you can expect to see using ultrasound in a power module. So first, I'm going to give you a few slides as an introduction to ultrasound. So let's have a look at that. So the first slide shows us three application types and the type of images that you can expect to get with using the Sonoscan system. The first one on the left is a bonded wafer. It's an optical image, and then the Sonoscan image underneath. And this image is of the bond interface. Bright regions are defects, in this case delamination and voids, and the dark region is where you have a good bond and where there's no problem. Quite a bad one. The second example is a plastic molded device, QFP, and on the Sonoscan image we've added color to the defects. So the red regions are delaminations, voids on the die surface, and we have some yellow. You can see some yellow as well around the edges here. There's some delamination just beginning on the die attach as well. This particular image is showing us the die surface. It's quite a critical area, and you don't want any delaminations there. Another bad one. So on the right we have a flip chip device, and if we image through the flip chip to the underfill interface, this is the kind of image that we expect to see. In this case there are a few things going on as well. There's you see this red dot, there's a void trapped in the underfill, and also there's some contamination. You can see the flow marks where they've probably injected it from this corner, and maybe flux or some other contaminant has got in with the underfill, and we're able to detect that as well. This next slide shows a comparison between X-ray and ultrasound, AMI. We're using the same sample, in this case a BGA device, and using the same resolution, same scan size if you like, and doing a comparison between both machines. So on the X-ray, obviously the X-rays are going all the way through, and we're seeing the solder balls in this case. There's a couple of defects here, a couple of shorts on a few of the solder balls, and the bottom right as well. So perfect for inspecting the solder balls on BGA device. With the ultrasound, we're seeing delaminations that the X-ray doesn't. The X-ray is just going straight through, and it's nowhere to be seen on the X-ray image. But on the Sonoscan, it's clear as day. With a void or delamination, ultrasound can't go through. So what happens is all of the energy is reflected back, and we can see it very clearly. In this case, we've added red to the delamination or voiding, and this void is at the mold compound to substrate interface. Substrate being the substrate of the BGA. Just going around it with the highlighter now. So between the black mold compound and the substrate level. So that delamination probably goes right underneath the die, and it's an electrical failure, and it's probably been caused by overheating, either from soldering, or it's been powered up and it's popped. So we're using between 5 and 500 megahertz. If you want to change the frequency, you need to change the transducer. This one is a 100 megahertz transducer with 1/2 inch focal length. You want to use the highest frequency you can to get the best resolution, but you're limited by the material that you need to penetrate. Just step on to the next slide here. So this will explain a bit more clearly that the higher the frequency, the better the resolution. But there's a bit of a trade-off because you get more penetration with the low frequency compared to the high frequency. So depending on the application, depends on what frequency you select. So now we come on to the practical example and actually see some images. So I'll be using our VRM software, Virtual Rescan Module, and what this allows us to do is work offline or away from the system. So I've previously done one scan on a power module and recorded the signal that we see here for every single pixel location. It's all been stored in one file and one scan from the system, and then with that file you can take it to a laptop, take it to a desktop and do your analysis away from the system. So let's bring up a couple of reference images, cross-sectional view, and then the optical view, a photograph of a power module. This is not exactly the same module that I scanned, but they're all similar in construction. What you need to remember here is I've scanned through the base plate, through the solder, through the ceramic, and then the last interfaces would be the top of the die. So I've imaged through the bottom side, and that's the easiest way for the Sonoscan to access all of the layers. So let's look at the first echo that I've recorded here, and I've started the timing or the recording of each pixel location, the signal of each pixel location. I've started the timing from base plate to solder interface. That would be the first echo that we see, and this is the image that we see. So if I just take away this one and zoom up make this one a bit bigger, it's just there's a preview image on the main window here, and then a zoomed image here. It's the same thing. There's some voids there between base plate and solder. These white regions are voids in the solder interface. Not too many, pretty good. And these markers, these are probably just manufacturing markers on the outside here. The uniform grey is where you have a good bond, and then the bright regions are the voids. So looking at the cross section, the next interface would be solder to copper. So going through the solder to copper interface, and let's refresh that. So there's some larger voids there that we've detected. Obviously the bright regions again are voids, dark regions or grey level is uniform bond. If I zoom back out again a little bit, we're not really getting a complete image across the entire solder. What's happening here is, if I just go to another image, let's go bring this image across, just put it over the top of the other ones. It's just an example. The solder layer can be warped, or not warped, but thicker in some regions than others, and mostly it's because of the warpage in the DBC layer. This is just the tilt this image is showing us, but there's a variation in solder thickness. So we're seeing that in our image here, where we don't get a uniform grey all the way across. So what we can do to overcome that is a couple of things. I mean, the basic way, or the easiest way, would be to make our window but larger. So you just open up the gate here, refresh. That basically makes a wider slice, if you like, so it's catching the echo in all positions now. Now we can see the complete solder to copper interface. Let's go to the next interface down, which would be copper to ceramic. That would be the next interface. So just go slightly deeper. And there's a couple more here. Let's go a bit deeper. Should come on to see the, we're now beyond the copper, the last final copper layer, and we're now copper to solder or die attach, and this interface is now showing us die attach. So let's improve that a little bit and get a bit more clarity on that, a bit more gain, refresh. So there's a couple of voids coming up now. Let's zoom up so we can see that more clearly. Bring that down. So there's a nice cluster of voids there and that die attach. What else have we got? We're having a bit of a problem here. We've gone beyond the die itself, and we can now actually see the wire bonds on the top of the die. These dark dots here. So what we could do to improve that, so we get a nice uniform image of the die attach, is to reference our triggering from the solder to copper echo. This one is moving all over the place, and all of these ones are moving in parallel with that. So let's switch on dynamic trigger. I want to trigger from this echo here. This is the one that's upsetting everything. And set gate, refresh. Okay, almost a good image there. Zoom out a little bit. So that's improved it considerably, and now that we have a nice uniform image across all of the die, we can use our automatic digital image analysis to evaluate each of the die and give you an output of voiding in a percentage, largest voids detected, total area of voiding detected, and that kind of thing. And you can output that as a Excel sheet or an image with accept and rejects on it. So let's now go to the final interface, which would be the top of the die. Let's switch off dynamic trigger for a minute. So I'll just refresh that one. Not too bad, and now we can start to see the top of the die and all of the wire bonds. So if any of those dark spots were missing, you could assume that the bond wires are not making contact, or missing completely from that region. So thanks very much for listening. That concludes this short video presentation on AMI. If you'd like more info, please get in touch. We'd be more than happy to help.